Yes, so let me introduce Donatella, our next speaker. She's a faculty of St. Andrews, and she's been working on Bose-Einstein condensate for quite a long time, and did some very good work in that subject. And today she's going to talk about, let me see, Bose-Einstein condensate in holographically generated optical traps.
So thank you very much for the kind introduction, and let me also thank Luigi and all of you organizers for putting together such an interesting, such an exciting event. We had Bill Phillips' talk last week. He said that his was going to be an enrichment talk, and indeed it was. But I would say that all our talks are enrichment talks, because we are all learning so much, and it's being so useful. So, so yes, my talk is going to be on ring traps, and we are many of us are interested in ring traps, and we have our Atomtronics review here. That is a very good summary of the more recent developments. Let me mention a few experiments, recent experiments. Recently, we've had the quantum interference of currents in an Atomtronic squid in the group of Malcolm Boshier. Squids are very useful, not only for fundamental physics, but also for applications like rotation sensing. And they can also be used as qubits, as shown here. We have seen recently supersonic Bose-Einstein condensates, and we have seen the simulation of an expanding universe in a Bose-Einstein condensate. So there are many more ring experiments, and there are so many different directions that one can explore. We don't need to consider just rings. We can consider coupled rings like this one, or stacked rings like this, or indeed racetrack circuits, as we've just heard in Charles' talk. So there are so many interesting, so many exciting directions. So in St. Andrews, we produce Atomtronic circuits by using a spatial light modulator that shapes the geometry of the atom confinement. So we engineer our optical traps with a spatial light modulator, and these are examples of what we do. So with the spatial light modulator, we can have a light. We can shape light in the shape of an atom guide, or a guide with a junction, or a ring, or this cross geometry. And these are images of the Bose-Einstein condensate trap in these geometries. In this talk, I will talk about the ring in particular, even though the other geometries also have its own merits. So, so what we want to do in these ring traps. Our main motivation is given by these two papers. The first by John Dowling on superposition of vortex and anti-vortex states to be used as a gyroscope, so for rotation sensing. And this second one by Veronica Haufinger is again superposition of vortex anti-vortex states for sensing of magnetic fields. I know it's not in the title, magnetic fields, but the paper does mention also magnetic fields. So, so this is our main motivation. This is what we would like to do in the future. So in this talk, what I will show you is how we can simulate the preparation and the subsequent evolution of a condensate in a vortex-anti-vortex superposition. So if I may step back a moment, so how do we produce one vortex state or circulating state in a condensate? You can stir a barrier in the condensate, or you can transfer, like here, the orbital angular momentum from a Laguerre Gaussian beam to the condensate wave function with a two-photon process. So this is a Raman transition. So the condensate undergoes a Raman transition under the influence of a Laguerre-Gaussian beam and then another Gaussian beam to complete the transition. And orbital angular momentum is being transferred from the Laguerre-Gaussian beam to the condensate wave function. Alternatively, one can do phase imprint, so-called phase imprint. And here we just pulse a light beam that has an especially engineered intensity distribution that looks like this. And what we do here is we have a space-dependent light shift, which during the pulse changes the phase of the BEC wave function. So the BEC wave function now has acquired this phase, where U is the light shift and tau is the pulse time. So these are different ways we can imprint. We can transfer angular momentum to our condensate. We could say that both these and these two methods, they're both phase imprint. Here, it is the phase of the Laguerre-Gaussian beam that gets transferred onto the Bose-Einstein condensate wave function, whereas here the phase imprint comes from this space-dependent light shift. So we use the intensity of the light here to imprint a phase on the wave function. Here we use the phase of the light. Currents, these vortex states can be detected, for instance, with interferometric means, which have been demonstrated with bosons, Bose-Einstein condensates to begin with, but in this conference, we've also seen it realized with fermions in Kevin Wright's talk and also in Giacomo Roati's talk. So this is one circulating state, one angular momentum state, but we want a superposition. So we want a superposition of vortex states. So experimentally, you can do that with, for instance, a Raman transition, but with more than one pulse. So we have a temporal sequence of Raman pulses, and you can use that to superimpose angular momentum states. So for instance, so this was done in these two papers, and this diagram here is taken from this paper here. So we have a first pulse with a Laguerre-Gaussian beam that goes like this. So that gives transfers this angular momentum to the BEC. So now this is our BEC wave function. But then after the second pulse, which is this one here, this LG beam is as a phase winding the other way, and we can therefore create a superposition or an interference, if you like, of angular momentum states that looks like this. So this is one way to do it with a temporal sequence of Raman pulses. Alternatively, and this was proposed again by John Dowling, this was a precursor to the paper that I mentioned earlier. Alternatively, you can do just one Raman transition like this from an internal state, initial internal state to a final internal state of the atom. But one is a Gaussian beam, one photon comes from a Gaussian beam, but the other photon comes from a superposition of Laguerre-Gaussian beams with two different charges, m and minus m. So in this paper, it was shown that you can get an effective transfer, to this final state, and the wave function of the condensate in this final state has acquired a superposition of phase windings. This e to the I m phi and e to the minus m phi, these are the two phase windings of the two Laguerre-Gaussian beams. So this is a superposition of phase windings, which can be written as this cosine of m phi. M is the charge of the vortex. And this is how you produce the superposition of vortex states. For instance, going back to this diagram here, this would be this wave function, cosine of m phi, well, the corresponding density distribution of this wave function this was for m equals to 1. So a superposition of m equals to plus minus 1 charges. So we would like to explore how to implement this scheme using a spatial light modulator. So this is what we have in our lab. We use a phase-only spatial light modulator. As usual, it's an array of pixels. So you illuminate the SLM with the Gaussian beam. And then this is a diffractive optical component. So we need to go in the far field of diffraction where we have Fraunhofer diffraction. And here we have the light fields that we can use to manipulate, to trap and manipulate our atoms. So it is possible to use more than just one wavelength of the light in this kind of experiment. So we can take this input laser beam and have different wavelengths superimposed, and then we can control different wavelengths separately from each other. And therefore, for us, it's convenient to try and do an experiment where we have a ring trap and the phase imprint beam all coming from the same SLM. So we want to control two separate wavelengths, which could be, for instance, in 1064 nanometers for the optical dipole trap and 780 nanometers for the Raman beams, assuming that we use rubidium. So therefore, a very brief aside on how we control different wavelengths independently, simultaneously with the spatial light modulator. Let me show you a brief aside on this. So the spatial light modulator, as I said, is a diffractive optical component. You can think of it as a generalized diffraction grating. And all the light patterns that we use can be seen as the first order of diffraction of our diffraction grating. So if we just consider now a simple diffraction grating, just made of lines, this diffraction grating will produce in the far field our orders of diffraction, so the 0th order, first order, second order, minus first, minus second, and so on and so forth. But diffraction depends on wavelength. The angle of diffraction grows with wavelength. So if we were to illuminate the same diffraction grating with two different wavelengths, lambda 1, lambda 2, lambda 1 being the longer, then the orders of diffraction would not be on top of each other. The blue light gets diffracted less, the red light gets diffracted more. But no, we want to work with different wavelengths on the same spot where the atoms are in our experiment. So the way to do it is to consider now a diffraction grating here that doesn't just have one period, but it has two periods at the same time. So we superimpose different periodicities in our diffraction grating. And then, let's say we superimpose two periodicities on our diffraction grating, then our first order here for a given wavelength, say the blue light, well, there's going to be two spots because we have two periodicities. And similarly for the red wavelength, there's going to be two spots because we have two periodicities. Now we can arrange the periodicities such that one spot at one wavelength superimposes with another spot at another wavelength. And that's how we can do it. So this is done here. And therefore this is, if we want to superimpose two wavelengths, this is the kind of target that you want. So here there are the two spots that I just mentioned. This is our target light intensity. We need these two spots. The center of the output plane is this cross here. That would be the 0th order of diffraction. It's not in the center of the plane, but it is the center in reality. And therefore, we produce these two spots of light. This is the hologram that will give you the two spots of light. And then if we take this hologram and we illuminate, this is what goes on the SLM. If we illuminate these with two different wavelengths, say 780 and 1064 nanometers, then each of these, so each wavelength will produce two spots. And this is what you have here. So here the blue light is the 780 light, the red light is the 1064 light. And as you can see, there is this spot here in the center where both wavelengths are in the same place. So we superimpose the two wavelengths. And here is this is the distance from the center, this R780, R1064. These are the two distances which give you the condition for this central spot here to have both wavelengths at the same time. So this is the principle. And now let me show you how one can apply it to the case of a ring trap and phase imprint. So this is what it looks like, and remember, we need to control to create these superimposed Laguerre Gaussian beams. We need to control both the intensity of the light, but also the phase of the light, because we need to produce phase windings and superpositions of phase windings. And therefore, that's what you have here. So this is the intensity of the light, and this is the phase of the light. We can control intensity and phase with the SLM. Details can be found here. And ignore the noise all over the place here. This comes from our hologram calculation algorithm. Is the price to pay to get really good results in particular areas of the output plane. That's where the atoms are going to be. To get very good results there, we have to let algorithm put some noise everywhere else. So, okay, so what do we have here? So here, the center of the output plane is up here in the corner, and therefore the idea is again the same. I have a ring trap, and I have the phase imprinting light here. But when I illuminate that line with the two separate wavelengths, I will have a ring superimposed with a phase imprint, which is what I want. So optical dipole trapping, of course, depends on the intensity. So here we put on the intensity plot, we have a ring of light. On the phase here, corresponding phase of the ring doesn't matter too much because optical dipole trapping does not depend on phase. Now, the phase imprint, here is the intensity for the phase imprint, and here is the phase for the phase imprint. And these, again, remember here, we need to superimpose two Laguerre Gaussian beams, and that's what you get if you do that. So if you superimpose two Laguerre Gaussian beams, you get an intensity dependence if you go around the center, which is the cosine square of m phi. So this is what we get, and this is the phase structure of the superimposed Gaussian beam, Laguerre Gaussian beams. So it goes with 0 pi 0 pi as the phase structure. Okay, to complete the Raman transition, you also need a Gaussian beam, but we don't simulate that because you can always add a Gaussian beam, just add it to the setup. There is nothing interesting about that. In this example, the vortex charge is ±2, so m here is +2 in this example, and therefore, by realizing these superimposed Laguerre Gaussian beams this way and this way, by doing the two-photon transition, you get your condensate in the superposition of ±2 circulating states. So, and this is what it looks like. So again, we can write, this is now the BC wave function, a superposition of the two circulating states. And this is now with m ±1. I'm afraid I'm not being very consistent from one slide to the next. I do change m, the chart, going from one slide to the next, so bear with it. So this is an example for it's a vortex anti-vortex superposition with the charges ±1 created as shown a moment ago. And what we show here is how would you sense rotation? How would you use this as a gyroscope to measure an applied rotation? So if you have an applied rotation, then the two parts of the superposition will acquire equal and opposite phases, and this part will acquire this e to the minus I phi phase, and this part will acquire the e to the I phi phase, and these are Sagnac phases. So the difference between these two phases is given by this expression here, where omega is the applied rotation, and this will give you a precession of the density pattern of your condensate. So basically what we have here is a standing wave of atomic density, because we have these two circulating states propagating in opposite direction, and this standing wave of atomic density undergoes a precession under an applied rotation. Let me emphasize here that on this slide and in all the subsequent slides, this simulation is done with no atom-atom interactions, so it's a single particle physics. We yet have to add atom interactions in our simulation. So, okay. So this is a way to create these states experimentally, but with a specialized modulator, we can do many different things. It's a very versatile tool. So another experiment that one can do is to do phase imprint on the BEC wave function, but we can imprint, for instance, a diffraction grating, and that's what we simulate here. So so here we have the same ring trap as before. That doesn't change, but what we have here, this phase here is different from the phase we had before. This is a phase that going around the center varies as this alpha cosine of gamma phi. So so this is like a diffraction grating with a period that is given by gamma, which is 2 in this example. So the phase varies over, there are two periods of phase variation as we go around, and this alpha is just the modulation depth, if you like. So if you do a phase imprint experiment, again Raman transition with the phase imprinting beam carrying this phase gets transferred onto the BEC wave function again, and therefore we end up with a wave function that looks like this at t = 0, straight after the phase imprinting is done. Let me also comment that here the intensity of the phase imprinting beam is chosen to be flat. You see just gray, and that's to be sure that when you pulse, you do your Raman pulse, you want a pi pulse condition everywhere around the ring. So you want a 2-photorabi frequency that has a constant amplitude around the ring, and that's why the intensity here of that beam is flat. Okay, so that's another way to do it, and that what the result looks like in the simulation. So we start from a Bose-Einstein condensate in the ring, and then we imprint the phase grating, and we imprint this phase grating, and as the condensate wave function evolves, you start seeing after some time these peaks developing in the condensate wave function. So this is the equivalent of the far field of diffraction of a diffraction grating for light. If you go in the far field, here we go after some time, you develop diffraction orders, and this is what we observe here. In this plot, again, we apply rotation, so we also observe these diffraction orders precessing under rotation due to the Sagnac phase. This is very similar. This result is very similar to this collective excitation interferometry, which was first done by Dan Stamperkorn, and which Gretchen Campbell also showed us last week. So this state here looks very similar to these phonons going around the ring in 2 different directions, because basically what we have here is this is not just a pure vortex antivortex state. It's not just one charge or plus minus that charge. It's a superposition of many angular momentum states that make up this. So again, going back to optics, you have all the orders of diffraction, not just 2. Okay, so this is another way that one could do the experiment. Let me show you one way another approach that we've been thinking about, and so I would like to make this general point that if you can shape the trap that confines the atoms, you can shape the amplitude of the BEC wave function by shaping the confinement. And then if on top of that, you can also do a phase imprint, which could be in principle any phase you like, then this enables you to control the BEC wave function in a very nice general way, at least in 2 dimensions, which is what we are considering here. So you can shape you can control, you can engineer the BEC wave function. So here is very simple. This is a very cartoonish example of this. Let's not think about rings for a moment. Let's think about a box potential. And let's say that in this box potential, I want to I want to put all my atoms in a particular excited state of this box potential. In this case, would be the third excited state in the example here. So, but I want to start from a Bose-Einstein condensate experimentally. I just want to put this Bose-Einstein condensate in the third excited state of its trap. So how would you go about it? I would start from a different potential to begin with, which is, in fact, it's the same box, but now I put barriers, regular intervals, and these barriers separate the box into little boxes, and this would be the ground state of each of the boxes. Now, these barriers should be tunneling barriers, so that in reality the wave function doesn't quite go to zero at the barrier, so it's not like in this cartoon, and this would also enable tunneling across the barriers, so that we have the same phase everywhere. So we want a constant phase. Now, if I start from a situation like this, then the experiment that you can do is going from here to here, very suddenly remove the barriers, and at the same time do a phase imprint. And the phase imprint here would be to put a phase equal to pi on this part of the wave function and this part of the wave function, and the pi phase will flip the wave function, that part of the wave function, so that the result is this. And this, in fact, is the excited state that we wanted to achieve. Now, this is just a simple cartoon. Well, if you like it, this is possibly another cartoon again. Slightly more realistic, though. This now applied to the ring. So we have a ring trap here, and we put these barriers. These are potential barriers, and we look at what happens. So we start with the condensate in this potential. So we have different lobes corresponding to these sub boxes, if you like. And then once we have our ground state in this potential, as I just said, very quickly remove the barriers and apply the phase imprint. So transform the potential to this, just the ring, apply the phase imprint, and this is what you get. So this is the atomic density. The lobes structure comes from the original potential, but what we also, with the barriers, but what we've done here is we also applied a phase imprint. And this is now very close. It's not exactly the same as a vortex-anti-vortex superposition, but it's very close. The discrepancy comes from the fact that we do not want the wave function to go to zero at the barrier. We do want tunneling, and this is what makes this not exactly the same as a vortex-anti-vortex superposition, but it's quite close. It's quite close. If you look, if we produce this state with this method, and then we look again at evolution in time, we can see that the state stays quite close to itself. It doesn't change very much. So this is very close to being a stationary state, which is what a vortex-anti-vortex superposition is. Let me mention, I'm almost done, by the way. Let me mention that this approach is has some similarity to this experiment here by Jérôme Begnon and Jean Dalibard, where they start with a ring condensate and they put barriers here, but these barriers are not tunneling barriers. So these are different parts of the condensate which are completely disjoint from each other. So there is a random phase going from one segment to the next. And in this experiment, they then merge the condensate. So they remove the barriers and they merge the condensate, but you still have these random phases. And these random phases then leads to this stochastic formation of supercurrents, which they observe experimentally. So this idea of the barriers is the same, except as we are thinking about here, except that our barriers are meant to be tunneling barriers, where we maintain a flat phase everywhere around the ring. So it's the opposite of what we had in this experiment. So Nick Bilgelow had a similar experiment a few years ago, where they took three separate condensates in a triple well potential, and then they merged the condensates by removing barriers, and again they found vortices being spontaneously produced in that system just from these random phases. So And this is pretty much with this. This is pretty much the conclusion of my talk. So so what do we want to do next? Well, of course, we want to do the experiment. Now, in terms of simulation, we would like to simulate an imbalanced vortex-anti-vortex superposition. Everything until now was a balanced superposition, so same number of atoms in the vortex as in the anti-vortex. However, the imbalanced superpositions are also interesting. For instance, for the magnetic field sensing that I just mentioned earlier, you do need an imbalanced superposition. And then for that proposal, you also need atomic interaction. So we should definitely add it to the simulation, and I believe that will make a huge difference. So we'll have to see what we find, and we think a lot the result. And so in terms of simulations, that's what we want to do. Then, as I said, we would like to do the experiment. So there will be clear experimental challenges, keeping the phase the same all around the ring so that you're then able to manipulate it. This is going to be a challenge. Kevin Wright last week did mention this in his talk, that experimentally it's really difficult to keep the phase flat and to be able to control it. And we will need tunneling barriers if we are to try this last scheme that I showed you. So just as a final point, everything here was done with a phase-only special light modulator. This is what we use at the moment, but actually a DMD, a digital micromirror device, can also be used to do almost everything that I have just discussed. And that's because phase imprint can be done with light intensity, like we mentioned earlier. And therefore, you can actually use a DMD to do some of the things that I just discussed. I just mentioned it because many groups are using DMDs more than phase-only special light modulators. And I think this is the end of my that's the end of my talk. Let me conclude by acknowledging the people who have done the work. These are the current members of my group. These are the former members, which do need an acknowledgement because we are still using the results of their work. And this is the end of my talk. So thank you very much for listening. And are there any questions?
Donatella, there is a question from Maxim.
Yeah, I mean, yeah, thanks. I mean, great talk, thanks. So you would probably expect this question from me. I know it's it would be an enormous step forward, but is your strategic goal macroscopic superposition of two vortices? Are you after a cat or not yet?
I think we're all after a cat, right? Not really. I think this is so what I've just shown you. This is not a cat. This is not a known state. What we're thinking about. So each atom in the condensate is independent of the other atoms. It's probably too ambitious to consider two macroscopic superposition like cat states. It's, to be honest, not within my horizon, but yes, we'll see where we go.
So how many atoms would you be able to? What's the minimal number of atoms would you be able to resolve in the experiment? What's the minimal number? So
because we assume
we see 100.
Well, we assume we have a condensate here to begin with, and when you do experiments with condensates, it's not easy to go to very low atom numbers. These are not single atom experiments or few atoms experiments. So I think with the condensate, you normally work, if you want to work with a very small condensate, it will be maybe 1,000 atoms. Okay. But that's probably very large if you want to create these non-classical stuff.
For 100, there might be hope.
Well, it's nice if you're only a factor 10.
Yeah.
You know, it's perhaps better than orders of magnitude. Yeah.
There is another question in the Q&A by Professor Carsten Angel.
Well, the question was about randomness. So one could also use a fixed random phase imprint. And when you repeat the experiment, what would you expect to happen? So I was thinking about this Jean Dalibard experiment where the phase gets random by some, I don't know, microscopic process. And here you would make it random in a controlled way.
This is something that one has to think about, because you need to. I don't think a random phase imprint in this case would be desirable if you want to create these nice vortex-anti-vortex superpositions. So this is a matter of well, do the experiment alongside the simulations where you put in this effect to test the robustness of the scheme.
Mm-hmm.
I don't see anything good coming out of it or anything interesting for this particular. So these random phases are obviously very interesting in the Jérôme Benyon experiment. That's what they study, but here maybe no.
Well, it's not on your agenda. Okay.
Gerhard, you can ask.
Okay, thanks a lot.
If it's a short question.
Thanks to Natalia for the great talk. In one of your final slides, you mentioned the DMDs as well. So if you would set up the experiment anew, would you take a phase only SLM or a DMD, or would you say the perfect combination would be having both?
Oh dear, I think when you've worked a long time with a system, you have a loyalty towards. I think I would want both for flexibility. I think in reality DMDs have I think they have more advantages than phase only spatial light modulators. They're faster, and the experiments I've just mentioned could be done with a DMD. If you want to produce the first scheme, the superposition of like Gaussian beams, I think you have to do that with a spatial light modulator, with a phase only spatial light modulator. You do need to control the phase for that. But for the other examples I had, you can do everything with a DMD. In fact, you can do everything with just one wavelength, because you can. The advantage of a DMD is that you can change your light pattern so quickly, and you can just phase imprint. I think you can almost do everything with just one wavelength, just by pulsing, just changing over time that one wavelength. I think you can do everything. So, yes, I would probably try. I would try both to hedge my bets. So.
There's one last question from Luigi. Luigi.
Yes, on macroscopic quantum coherence, so on the cat state. Okay, so I understand that actually your system is non-interacting, so the system is single particle. Okay, but then I mean, in what sense you say it's too ambitious to go to the cat state? So what do you say? So I think there are certain regimes in which there are predictions in which the wave function is the cat state, right? So it's known predictions. So you should go to the 1D regime. Then I mean, people study fidelity, and I mean there are certain regimes in which the wave function is a cat state. So you have a macroscopic quantum coherence. Of course, you have to insert an impurity, a localized impurity somewhere. Otherwise, you cannot obtain. So the state is not stable. Mm-hmm. So you need to make it. So I think, so then, I mean, can you comment a little bit more? So what do you think about too ambitious to create a cat state?
The truth is I haven't thought about it. I haven't thought about it yet. So my thinking there is a little bit superficial. You always hear proposals that do work, but then if you lose, it's enough to lose a few atoms and that's it, it's gone. And so, but as you can see, I haven't given it enough thought yet. And so it was definitely something that we could consider. So this is something we'll consider in the future, definitely. So thanks for the encouragement.